Section 2.3 Characterization of Invertible Matrices. So we have a theorem called the invertible matrix theorem, and we abbreviate it like AIMT, and this is an important theorem. So you have to see how the things are interlinked here. So it says that let A be a square matrix n by n size, then the following statements are equivalent. That means for a given A, these statements are all true or all false. So if one statement is true, all of them are true. And if one is false, all of these statements are false. Okay, also note if A and B are square matrices such that AB is equal to I. So at the end of the theorem, I'm reading the statement. So if A times B is equal to I, so if two matrices multiplied, square matrices being multiplied, and the result is the identity matrix, then both A and B are invertible and they are inverses of each other. Okay, what do we mean by invertible linear transforms? We saw what linear transforms are. They are transforms are functions which satisfy this property, that if we say T is a transform, then T of x plus y will be equal to T of x plus T of y. That is one condition for a transform to have for it being a linear transform. And the second one is T of Rx is equal to R times T of x. Now these two statements not every function or every transform obeys these two conditions or satisfy these two conditions, but the ones that do are called linear transformations. And now we are going to say or mention when is a linear transformation invertible. Invertible means when does it have an inverse. Like functions, when you learn the functions and their inverses, so not every function has an inverse. There is a restriction on the functions which can have an inverse. So a linear transformation T going from Rn to Rn is said to be invertible if there exists a function s from Rn to Rn such that s of T of x is equal to x and T of s of x is equal to x as well. So if we do apply one transformation, we get something, and we now apply another transformation, the other transformation on that, and we go back to where we started. That's what we are looking for. If such an S exists, then it is unique and must be a linear transformation. Okay, so S is also has to be a linear transformation, and it will be a unique, and it is actually the inverse of the T transformation, which is the what you call it is the inverse of the linear transformation T. Okay, so next thing, so theorem, another theorem, let T be a transformation then from Rn to Rn be a linear transformation and A be the standard matrix for T. That is, T of x is equal to A of A times x. Then T is invertible if and only if A is invertible. So in order to check whether a given transformation is invertible or not, or in other words, if an inverse exists for that transformation or not, what you need to do is figure out what is the standard matrix for the transformation and then check if that matrix is inversible. So which means means if the inverse of the matrix exists. So here we say, okay, in this case the linear transformation S given by S of x will be A to the negative 1A. So A inverse x. So remember, this is like we can find the S or the inverse transformation by multiplying the x by A inverse instead. In the direct transformation in T, we are multiplying the x by A. Here we multiply by its inverse. Okay, so that is the information, and let's see now the questions or examples that we will go over, and most of the in this section basically depend on the statements that you saw in the invertible matrix theorem. So it will be a good idea to have the IMT in front of you so that you can answer these problems. Okay, so first example is mark true or false. So just put a T or a F, justify each answer. So just a small sentence to why you can say it's false or why you can say it is correct or true. So first one, if there is an n by n matrix T such that A times D is equal to I, then D times A is equal to I. So this is correct. So true. A is true. And the reason is that if they are inverses of each other, for it to be an inverse, it is kind of necessary that this happens. Also note here, if AD is equal to I, so add from the note below the IMT, it says when A times B is equal to I, then A and B are both invertible. So if A times D is equal to I, then A and D both are invertible matrices because they are square matrices. And okay, so here we are assuming that A is our square matrix n by n, and then now we are taking the D to be an n by n matrix as well. So A times D is equal to I, and then D times A is equal to I as well. B part, if the linear transformation which takes x to ax maps Rn to Rn, then the row reduction echelon form of A is I. So let's go back to the statement and the IMT. So if you notice here, the linear transformation x to A, which maps x to ax, maps R onto R, Rn onto Rn, not Rn to Rn. Okay, so the I statement of the, I hope you guys can see that, the I statement, it is saying Rn onto Rn, not just on to Rn, but onto. Okay, so that's why this is not correct.